Okay, so by adding more rectangle, we can approximate, or we can have a better approximation of the area below the curve. Yeah, this is the illustration. We are adding more and more and more and more rectangle. Yeah. Okay, the question is how much rectangle that we need to add until we have a good approximation. That's the question. Yeah. Yes, we know that adding more rectangle will give us better and better approximation. The question is how much? How much rectangle? Okay. How many rectangle that we need to add? So the answer to that question is we are using as much as possible, as many as possible rectangle. Therefore, we take the limit of number of rectangle to infinity. Yeah. So I will go back again to the slide. Yeah. Okay, so how many rectangle? The bigger, the more rectangle in here to have, in order the more rectangle will give better approximation. Yeah. Therefore, the exact value of S, yeah, in here, the exact value of S will be the exact value of S, or the area below the curve, is given by S equal to, so this is our sum of our rectangle from I equal 1 until N, yeah, of delta X. This is the base, yeah, and then this is the height, Fxi, okay, and then we take the limit of N goes to infinity, yeah. So this is the exact area of S. Okay, let's see the example here. Previously, we already know that Fxi, yeah. So given in here in our problem, delta X is 1 over N, yeah, not, yes, 1 over N, right? In our case, given A is 0, B equal 1, Fx equal x squared, yeah. Then we have delta X, yeah, this is the area that we already have before, yeah. The area that we already have before from the first example. This one, yeah, this is the area that we want to calculate. And then it's given that A equal 1, A equal 0, B equal 1, Fx equal x squared, and we want to approximate, or we want to calculate, yeah, the area below this curve. Therefore, we have 1 over 1 minus 0. So this is came from 1 minus 0 over N. Yeah, this is 1 over N. And then what about Xi? Yeah, you need to know what is Xi. Previously, we already know that. So this is the illustration. If we divide, yeah, interval from 0 until 1 into uniform, into n uniform partition, yeah, this is 1 over N and 1 over N, yeah. So this is, let's say this is x0, this is x1, x2, x3, and so on until this is xi, yeah, and the last in here, this is xn. Okay, so what we need is the general form of xi in here. What is general form of xi? So we have that in here x0 is 1 and x1 is x0, the previous node, plus delta x, right? Delta x. Therefore, we have 1, sorry, x0 is 0, yeah, not 1. X0 is 0, and in here we have 0 plus delta x. 0 plus 1 over n, yeah, which is 1 over n. Again, x2, what about x2? x2 equal to x1 plus delta x, which is x1 is 1 over n, plus delta x also 1 over n. So this is 2 over n, right? And then what about x3? x3 is x2, previous node, plus delta x. That is 2 over n plus 1 over n, 3 over n. So as you can see, the pattern in here, you see here, is this is x1, 1 over n, x2, 2 over n, x3, 3 over n, and x4, you can guess, it must be 4 over n, yeah? And what about xn? xn is n over n, that is 1. That is exactly the same like we have in here, yeah? And finally, we can, from this observation, we can have xi is I over n, yeah? Therefore, now we have xi is I over n. Okay, so the area of S, S equal to limit n goes to infinity sigma from start from 1 until n, yeah. Basically, this is not matter. It doesn't matter where your I start, whether it's from 0 or from n. I will start from 0, yeah. And then we have delta x multiply fxi. Okay, so basically in this sum is called Riemann, yeah, Riemann sum. Yeah, the Riemann sum is this value. Okay, Riemann is the name of the founder of this method. His name is Bernard Riemann, and he introduced this approach to calculate the area below the curve. Yeah. Okay, let us continue. Now this is limit of n goes to infinity sigma 0 until n. Delta x is 1 over n. Fxi is xi square, right? Yeah, from our problem. And then this is same as limit n goes to infinity sigma 0 until n, 1 over n, xi. So previously we already know xi is I over n squared. Yeah. Therefore we have in here limit n goes to infinity sigma I start from 0 until n, 1 over n, I square over n square. Yeah. And then we can simplify this. Limit n goes to infinity sigma from 0 until n, I square over n cubic. Yeah. Look at this, because the sum depend on the value of I. Therefore, the value of n in here is a constant. Based on the property of sum notation or sigma notation, we can take n outside, yeah, n cubic outside the sum, and then it leave out with I square. Okay, so the I square in here, we already have the special sum before from our previous special sum. This is nothing but n goes to infinity, 1 over n cubic, and this is n plus 1, 2n plus 1 divided by 6. Yeah. Okay. So it leave us with the limit, yeah, with the problem of limit goes to infinity that you already know before. Okay, let's continue our calculation. We can simplify this first. This is n, 6n cubic. This is n squared, 2n cubic, right? And then you have 3n plus 3n squared plus n, yeah? Remember how to calculate this? Yeah, you don't have to worry too much in here because when you're dealing with a limit of n goes to infinity, so what you need to observe in here is the biggest power, yeah, the biggest power from numerator and the biggest power from the numerator. And the result is, because this is the same, so you only consider the coefficient in here, which is 2 over n, 2 over 6, yeah, and that is 1 over 3. So this is the exact value of s, okay? So basically this is the definition of integral, yeah? So look at this. The definition of integral, you can read in here, but basically the definition of integral, of definite integral, is limit of Riemann sum, yeah? So we are now can state that if fx is, okay, so if S is the area, definite integral, definition, yeah. So in short, definition of definite integral is the integral of a until b of fx dx, yeah, equal to limit of n goes to infinity of the Riemann sum until n sigma of delta x of fx. Yeah, this is definition of definite integral. So the previously, our problem previously, it's same as a 0. Yeah, in our case, from our calculation, that is integral of 0 until 1 of x squared dx is our previous calculation, limit n goes to infinity sigma I from 0 until n 1 over n, this is our delta x. Fx is I over n squared. And we have the result, which is 1 over 3, yeah. Okay, that is the Riemann sum, yeah. And definition of definite integral. So in general, if you have, yeah, you can calculate if we have in general in here, the integral of a until b fx dx, it has, so you can determine the delta x equal to b minus a over n, and then xi is a plus I delta x, yeah, and then yeah, you can basically put based on this, then we can have this one become limit n goes to infinity sigma 1 until, oh sorry, 0 until n, yeah, b minus a over n, a plus e delta x. Yeah, it depends on what is your f. Okay, so you can try another example later. Yeah, is as it will be your exercise for later. Okay, let us continue to the first. Let us continue to the first fundamental theorem of calculus. Okay, you can consider this example. Suppose, so I will take the example from the, I will take the illustration from the physics, which is the velocity and the distance traveled by some particle. Yeah. Suppose in here v denote the instantaneous velocity, yeah, or kecepatan sesaat, and st denote the distance traveled after t time. Yeah. For every t, the distance traveled from the interval, yeah, at the interval t until t plus delta t, you can calculate like this. Yeah, the distance traveled is st equal the velocity multiply t plus delta t minus t. Okay, so you can think of the velocity is the difference in s divided by the difference in time, right? The velocity is the difference in space, in distance traveled divided by the difference in time. So you can multiply velocity with the how much time needed to reach that distance. Yeah. Therefore, t minus t become the velocity multiply delta t. Okay, so if we change our t until to 0 until t, we can approximate the value of st become like this: vt1 t1 minus 0, vt2 t2 minus t1. So this is our delta x or delta t in here, and then so on until vtn t minus in here actually tn, yeah, tn minus 1, and then we have the sigma, yeah, I from 1 until n from vti multiply delta ti. Okay, so this is the Riemann sum for a function vt at 0 until t, yeah, from interval 0 until t. Then if the velocity is continue, we can approximate the area or the distance traveled by those particles is integral 0 until t vu du st in here. with the initial distance traveled is 0. Okay. But in here, we know that velocity is the derivative of distance traveled, right? Perubahan jarak, or derivative of distance with respect to derivative with respect to t variable. Therefore, we can write also Vt in here, derivative of s. Previously, we already know s in here, 0 until t, Vu du. Yeah, because from this expression, then we have the first theorem or first fundamental theorem of calculus. So look at this. So the derivative of integral of velocity is velocity itself, or it's same as the integral of some function. So first you have a function here, v, you integrate, or you take the integral, and then you take the derivative. Then it will be back to the original function, right? It seems like it never moved from the first position. Yeah, you take you have the function, and then you take the integral, but you take the derivative. It's like you take the integral, yeah, you take up, yeah, you naik, and then derivative turun, right? Yeah, so it's like you are not moving. It's like you are not moving from the original position, which is the same function. Therefore, this is our first fundamental theorem of calculus. If f is continuous function on interval AB, and for every x element of AB, and we have the big F fx as the integral of a until x ft dt, then we have the derivative of f is the function of fx. Or we can say that the derivative of a function, yeah, integral, yeah, derivative of integral of a function is a function itself. Okay, so that's the main point in here. Yeah, when you have variable in here, whether this is ddx, the important thing in here, the variable in the square must be the same. Then you have the variable in the square. Yeah, or we can say that every continuous function has antiderivative, or it's integrable, right? So that is the important thing. Every continuous function is integrable. Okay, let's see the example here. Find f prime x from the given function. Number 1. So the first fundamental of calculus, yeah, again, it roughly says that if you have derivative of some function, fundamental theorem of calculus. The first, yeah. It roughly say that the d square of some function of integral of some function. This is a until squared in here. Ft dt is equal f squared in here. Yeah, let's see the example. Suppose I have the following function. Find f prime x of this f of x integral 1 until x t cubic divided by 1 plus t squared dt. Okay, so basically this is our ft or our function. This is our function ft. Yeah. Then if we want to take the derivative f prime x or d dx of integral, so fx, right? So this is integral of 1 until x t square over 1 plus t square dt. Yeah, this is our integrand. It's same as by fundamental theorem of calculus, or I will put is FTC. Yes, FTC1. By FTC1, we can say that we have that is equal with x cubic over f prime x in here, 1 plus x squared. Yeah, that's it. Okay, that's the first. You can try the same for number 2, number 3, number 4. What about number 5? Number 5 is quite different here. Yeah, number 2, number 3, and number 4 is the same like number 1. You can try it yourself. Yeah. And now, okay, so basically number 4 is not the same. Sorry. Number 2, number 3 is the same, but number 4 is not the same. Yeah, let's see number 4. Find the first derivative of fx 1 until x, but in here there is x t dt. Okay, that's different. There is x variable here. So the first derivative f prime x is same as d dx of f, yeah, which is d dx of integral 1 until x t dt. Yeah, because the integral is respect to t variable, so x in here is constant. We can take x outside the integration. T dt. So we have the multiplication of two functions now. So you remember that? So we need to apply the multiplication rule for derivative, which is d dx of x multiply this function plus d dx of the integral 1 over x 1 until x dt multiply x. Okay, so d dx of x is 1. This is not changed. Plus this one by the FTC1, yeah, it's become x dx, become x multiply this one, x by fundamental theorem of calculus 1, yeah, and then we have 1 until x t dt plus x squared, yeah. So this is the final result. Then we have f prime x is 1 over x until x t dt plus x squared. Okay, that's for number 4. Yeah. Okay, what about number 5? Number 5, 1 until x squared sin t here. Or let us continue to number 6, it's the same. Yeah, 1 until x squared plus x given fx x squared plus x, and the integrand is square root of 2t plus sin t dt. 2t plus sinus t dt. Okay, so applying the derivative, it's same as d dx of f, and our f is integral in the form of integral 2t plus sinus t dt. Okay, so you cannot directly use the FTC or fundamental theorem of calculus, because in here the derivative respect to x, but in here we have x squared plus x. Therefore, you need to assume or make the bridge in here. Yeah, let u be x squared plus x. Yeah, so in here the FTC does not apply directly, because in here x, in here x squared plus x, which is different. Yeah, therefore you need to make a bridge in here using another variable u, and then we have and then you need to calculate also u prime or du dx become 2x plus 1, right? Therefore in here df dx, yeah, remember the chain rule in here. Yeah, we apply the chain rule. First, we going through u first, df du, and then du dx. Yeah, using the chain rule. So this is nothing but d du of 1 until u, because now we already assume that x squared plus x is u. This is still the same. 2 times t plus sin t, and then multiply du dx, 2x plus 1. Yeah, applying FTC now, the FTC is applied. Yeah, FTC 1 by fundamental theorem of calculus 1. We already have u and u in here. We have that square root of 2u plus sin u multiply 2x plus 1. Okay, and then yeah, you can change u. Let us change u into the original value, x squared plus x plus sin x squared plus x. Yeah, and in here we have 2x plus 1. That's it. So this is our f prime x. Yeah. Okay, so I will leave the rest of the problem to you as the exercise. Yeah. And for number 6, number 7, and number 8, you need to use the theorem, yeah, from integral, property of integral, or integral property in here. So we know that the integral of a until b of fx dx is same as minus b over a fx dx. Yeah. Or the second, if C is element of interval A until B, which is not same as A and B, then yeah, you can calculate integral of A and B f x dx the same as A until C plus C until B, right? Yeah, that is the second property of integral. And also you have the third property, which is suppose I have A until B x plus gx dx. It's same as A until bfx dx plus A until b gx dx. Okay, so there are three important property in integral. Yeah, in a definite integral, you can apply this property to calculate the next exercises. Okay, that's it for the first fundamental theorem of calculus. Let us continue to the second fundamental theorem of calculus. There are two fundamental theorem in calculus. The first one is already you have seen before, yeah. Okay, let's see the second fundamental theorem of calculus. Previously, we can calculate integral of fx 1 until x t cubic dt, yeah. So using the fundamental theorem of calculus, you can derive this, yeah. F prime x is x cubic, and then if we have okay, so this is same as x cubic can be expressed as derivative of x power 4 divided by 4, right? So it's same as the 4, yeah, it's same, it will be have, it will, so we will have x cubic from this derivative. Then, so we can also write d dx of x power 4 divided by 4 equal to d dx of the first form, yeah, 1 over integral of 1 until x t cubic dt. Therefore, we can take the difference in here, yeah, take the difference in here. So remember the theorem that say if we have two functions, that which derivative of those two functions is the same. Therefore, those two functions is only differ by a constant. So it's the same in this case. We have two functions, x power 4 over 4 and 1 until x t cubic dt, yeah. These two functions has the same derivative, which is x cubic. Then it meaning that this function, if we take the difference of the original function, this one and this one, only differs by a constant. Okay. Now, if we put here, we can write fx again, yeah, back fx equal this, and then we move this one to the right. So we have x power 4 over 4 plus a constant in here. Okay. Now, if we put x equal 1, then the value of f1 is 1 until 1, right? So this is 1 until 1. Actually, or basically, there is no area that we can determine, yeah, because the interval is 1 until 1. Therefore, the area is 0, or f1 is 0, yeah. Therefore, we have x power 4 over, so we have our x is 1, yeah, 1 over 4 plus k. Therefore, our k is, yeah, our k is minus 1 over 4 because it will be 0. And then we can write back this x, this 1 into x, fx 1 over x t cubic dt become x power 4 minus 4 minus our k is 1 over 4, right? Therefore, we can put, if we change our x become 10, yeah, we will have this value, or it's nothing but the value of the right boundary minus the value of the left boundary, yeah. Or if we change, this is a and b, it will become fb minus fa. So basically, it will this will our foundation. It's become our foundation of the fundamental theorem of calculus number 2. Yeah. Okay, I will straight forward to the theorem. Suppose f is continuous function and big F in here is the antiderivative of small f, which is f prime of big F equal small f on the interval AB. Therefore, the integral of AB fx dx, small f x dx, equal to the value of big F at x equal b minus the value of big F at x equal a. So this is the fundamental theorem of calculus. Yeah. Then, yeah, to conclude the result, we have the two fundamental theorem. The first fundamental theorem of calculus, it says that the derivative of integral is the function itself. Yeah, it go back to the original function. And the integral of a until b small f x dx is big F evaluated at x equal b minus the big F evaluated at x equal a, where big F is antiderivative of s, which is the f prime equal to small f. F prime of big F equal to small f. Yeah. Okay. So using this fundamental theorem, yeah, using this fundamental theorem, we can check our calculation. Yeah. We can check our calculation of the previous one. Previously, we already here. Yeah. So I will write again in here. Second fundamental theorem of calculus. Or FTC2. It says that if f prime equal small f, then integral ab fx dx same as f big F b minus big F a. Yeah. So we can check our previous calculation. Yeah. So using FTC2, calculate or evaluate the following integral. So previously we already calculate this one. Yeah. You already know this. So using basic rule integration. Yeah, this is our n. It's same as 1 over 2 plus 1 x power 2 plus 1. And then our boundary, so take the boundary here. And the same as 1 over 3 x cubic from 0 until 1. Yeah, by the second fundamental theorem of calculus, we know that this is 1 cubic, 0 cubic, same as 1 over 3. So it confirmed our result before. Yeah, our previous calculation using limit of Riemann sum, we determined that this integral is 1 over 3. And using second fundamental theorem of calculus, also it equal 1 over 3. Of course, this way give us more advantage. Yeah, the first way is not simple because it include the limit and the Riemann sum. It cumbersome to calculate. Yeah, and it also take more time. But in using the second fundamental theorem of calculus, it just the integral, and you can have the same answer by using short calculation. Yeah, by applying just short calculation. Okay, I will give you more exercise for this. Yeah, you can apply the fundamental theorem and the basic integration rule that we already discussed last week or yesterday. And so let me give you another example. Calculate the integral 0 until 1 of 2x x squared plus 4, for example. Yeah, dx. Yeah, obviously it cannot apply or the basic integration rule cannot apply directly in here because the integrand is not equal in with here, the variable of integration. So you need to use the substitution method. Yeah. Okay, so here let us assume that u is x squared plus 4 and du is 2x dx. Yeah, and then you can have integral of 2x square root of u. Yeah, and then we have dx, and 2x dx will be equal square root of u du. Yeah, du. Now you have that integral is equal to power half du. It's nothing but 2 over 3 of u 3 over 2. Yeah, and this is the same as 2 over 3 2 over 3 x squared plus 4 power 3 over 2. So this is your calculation, yeah, or abstraction. Then the complete answer of the problem is dx is 2 over 3 x squared plus 4 3 over 2, and put x from 0 until x 1. Yeah, and we have in here 2 over 3 5 power 3 over 2 minus 4 power 3 over 2. Yeah, so that is our final result. Okay, so now we already have first fundamental theorem of calculus. Okay, the second theorem, fundamental theorem of calculus, definition of integral, and then the series or the sigma notation. Yeah, You can read again from the beginning. Yeah, and don't worry if you feel confused about this. You can take the record and you can watch the record of these lectures, and then you still can ask a question in using Google Classroom. Okay, so until here, is there any question that you want to ask?